We are dealing the theories of classical statistics, and in this regard, in the previous lecture, you have seen the meaning of partition function in case of a classical system. In other words, you can say, considering the Maxwell-Boltzmann distribution law, we have defined a very important parameter or very important quantity which actually denotes how energy of a system is distributed in different levels, and that very quantity is called partition function. And you have actually find the expression for the partition function, or you can say the meaning of partition function, on the basis of Boltzmann distribution law. Okay. Now, after getting the concept of Boltzmann partition function, today we are going to know the expression for different thermodynamical quantities or different thermodynamic functions in terms of partition function. Actually, this is a very important concept. We express the different thermodynamic variables or functions in terms of partition function, and that is used variously in different theories of statistical mechanics. In this regard, the most important result is for entropy. It means, first of all, we are going to express entropy of a system in terms of partition function. Okay. Actually, you have already studied previously a very important entropy theorem which is called Boltzmann entropy theorem. And you know, according to this theorem, entropy of a system is defined like this. This is S equal to K ln W. We have studied this result in the previous lecture. You know, here this K is actually Boltzmann constant. And what is this W? You know, this W is actually the maximum thermodynamical probability of the system. Or in other words, you simply say that W is nothing, this is simply the maximum number of microstates corresponding to the most probable macrostate. Okay? This is W. You have already discussed this result previously in very detail. So I hope you have definitely this result is in your mind. So S equal to K ln W. Actually, starting from this formula, we will find the expression for entropy of a system in terms of partition function. So you can see, if your aim is to find the expression for entropy of a system, definitely you will have to find first of all the value of this ln W. After getting the value of ln W for a classical system, we will simply multiply that value with Boltzmann constant K and we will get the expression for entropy. Now, while dealing with the problem of Maxwell-Boltzmann distribution law or the Maxwell-Boltzmann distribution function, you have considered there is a classical system of system consisting of a large number n of particles, and those particles were non-interacting, or we simply say that they are weakly interacting, governed by the same Hamiltonian. Okay, and these particles were distributed in different quantum states. You have considered that n1 particle, each with energy E1, was distributed in G1 quantum state. Okay. Similarly, we have also assumed that n2 particle each with energy E2 is distributed among G2 quantum states. We also call this G1, G2 that degeneracy of these energy states. That is, G1 is called degeneracy of energy state E1 and G2 is called degeneracy of energy state E2. Okay. Actually, Considering such an isolated system, we have obtained earlier while dealing with the problem of Maxwell-Boltzmann distribution function that in how many ways these particles can be distributed among these different quantum states. Actually, the maximum number of possible ways in which all these n particles can be distributed in different quantum states, that is called the number of microstates corresponding to the most probable macrostate n1, n2, so on. Okay. Already we have obtained. So I am here writing the expression which was obtained earlier while dealing with the problem of Maxwell-Boltzmann distribution function directly. You have obtained earlier that this probability W is equal to n factorial times pi over I. Pi actually represents this is just the sign of product. Gi to the power ni divided by ni factorial. Actually here this is assumed that ni particles each with energy Ei are distributed in quantum states Gi. Okay. So I have written this result directly because I have already proved or explained this result earlier in the lecture on Maxwell-Boltzmann distribution law. Okay. Now, according to Boltzmann formula, when you have to find the expression for entropy, that expression is K ln W. So we must know what will be the value of log W. Okay. W is defined in this manner, and so what will be ln W? Ln W, you can see this will be log n factorial plus, as you know, when you will take log, this sign of product will change into sign of summation. So this is summation over I, okay, summation over I, and log Gi to the power ni. But you know that log Gi to the power ni, that will be equal to ni log Gi, okay, and minus log ni factorial, because ni factorial is in denominator, so this will be minus log ni factorial. Okay. Now you can see I have told you earlier that in each theory of statistical physics we need the use of Stirling formula, and you can see here how we can evaluate log n factorial and log ni factorial. Definitely you can say, because you have studied already in the previous lecture, a very important formula or a very important theorem or a very important approximation which is called a Stirling formula or a Stirling approximation. So here we will simplify these two terms of factorial terms by using the Stirling formula or Stirling approximation. So you can say this ln W will be equal to what? As you know from a Stirling formula that ln n factorial is equal to n ln n minus n. Okay, you know. And this is summation over I. The term ni log Gi remains at is, and again we will use to simplify this ln ni factorial from a Stirling formula. We know that this will be equal to ni log ni minus ni, but since here is minus sign, so the sign will be just reversed, so this will be minus ni log ni plus ni. Okay, this sign of summation is implied on all these three terms. Okay. Now let us simplify the RHS of this equation to a little bit. You can see here that this is n ln n minus n plus summation over I ni log Gi minus ni log ni, and the third term will be summation over I ni. But as you know, this summation over Ni means what? This is actually the sum of number of particles in different energy states. That is, this is simply equal to N1 plus N2 plus so on. Okay? And when we will add all these number of particles, we will simply get the total number of particles. So this N is the total number of particles. So instead of summation over Ni, I have written here this N. And you can see this minus N and this plus N will cancel out. Okay? And so our result is log W equal to N log N plus summation over I Ni log Gi minus summation over I Ni log Ni. Okay? Now, by using the Maxwell-Boltzmann distribution law, we can find the value of Ni, or what is the value of Ni in accordance with the Maxwell-Boltzmann distribution law. You have already studied in the previous lecture. As you know, according to MB distribution law, that is Maxwell-Boltzmann distribution law, the occupation probability, which is denoted by the symbol F of Ei. What is this F of Ei? You know, you have studied it. This is called occupation probability. And what is this occupation probability? You know, this is average number of particles per quantum state. As you can see, in Gi quantum states, the number of particles present is Ni. So in one quantum state, what will be the number of particles present? That will be Ni divided by Gi. And this number of particles per quantum state is called occupation probability, and this will be equal to F of Ei. So F of Ei can be written as Ni over Gi. And from MB distribution law, we know that this is equal to e to the power alpha times e to the power beta Ei. Okay? And so from here you can find this Ni. This Ni will be equal to Gi times e to the power alpha times e to the power Bei. Okay? Now we will substitute this value of Ni in this equation 1 at the place of this Ni. In fact, Ni is present here too. Here also Ni is present. But we will replace this last Ni by that result. Then the simplification will be easier. Not put the value of Ni wherever it is present. Okay? Only in last term. So let us see. When we will substitute instead of Ni this much in last term, what will be our result? This will be log W equal to N log N plus summation over I Ni log Gi minus summation over I Ni log Ni. No, but here you can see instead of Ni I have written Gi into e to the power alpha into e to the power beta Ei, which we have seen here. Okay? Now we will actually simplify this last term. The first two terms is at is, you can see, this is N log N plus summation over I Ni log Gi. And since here there is a product of three quantities, this is Gi e to the power alpha and e to the power beta Ei. So when you will take its logarithmic value, that will be simply sum of the log of Gi e to the power alpha and e to the power beta Ei. So what will be the first term? This will be, since minus is here, so all terms will be minus. So this is minus summation over I Ni log Gi. Okay? Minus summation over I Ni log e to the power alpha. But you know log e to the power alpha will be alpha, because this is alpha log e, but log e is equal to 1, so this is simply alpha. Okay. So here this second term will be summation over I ni times alpha, and again in the last term will be what? This will be ni log e to the power beta ei, but log e to the power beta ei, that will be beta ei into log e, and log e is 1. So this will be summation over I ni times beta ei. Okay. Now you can see this term, second term, which is plus summation over I ni log gi, and the third term is minus summation over I ni log gi. Both will cancel out. Okay. So what are the remaining terms? You can see these are n log n minus alpha n. Actually here this alpha is independent of summation. So alpha will be outside of the sign of summation, and summation ni represents the total number of particles, and that is equal to n. So this is alpha n. Okay. And here this beta will be outside of the sign of summation, and so the remaining factor is summation over I ni ei. Okay. Now again you know that this summation over ni ei, this represents the total energy of the molecules of the assembly. Why? Because this summation will be equal to n1 e1 plus n2 e2 plus so on. Okay. Actually you know that in n1 particle each have energy e1, and similarly in n2 particle each has energy e2. So the total energy of n1 particle will be n1 e1, total energy of n2 particles are n2 e2. So the total energy of the all particles of this assembly will be equal to sum of n1 e1, n2 e2, n3 e3 and so on, and that is equal to summation I ni ei. So this represents actually the total energy of this assembly. Okay. So instead of this summation over I ni ei, I have written here E. You can see. So log W is equal to n log n minus alpha n minus beta ei. Okay. Now we will evaluate this alpha in terms of A, which this symbol was already used in Maxwell-Boltzmann distribution law. You can see that we have written earlier that e to the power alpha is denoted by the symbol A. Okay. So if we will take log both sides, so this will be log e to the power alpha, and that will be equal to log A. But log e to the power alpha, you know, this is equal to simply alpha. Okay. So alpha is equal to log A. So in this equation, this alpha will be now replaced by log A. Okay. So at the place of alpha, we will write log A. And what will be your result? You can see. This log W will be equal to n log n minus n log A minus beta E. Okay. Now you can see in first two terms n is a common factor. So let us take this n as a common factor. And so this will be n log n minus log A minus beta E. Okay. But log n minus log A, this can be written as log n by A. So the first term is n log n by A minus beta E. This is second term. But you have studied in the previous lecture that this n by A is what? This is actually equal to Z, which is called partition function. You have watched the previous video, and you can see there that this n by A is called partition function, and it is denoted by the symbol Z. So instead of this n over a, I have written Z. So log W you can see is equal to n log Z plus e by kt. Why plus e by kt? Because you know beta is equal to minus 1 by kt. So this second term will become e by kt. So this is the expression for log W in terms of partition function Z. Now as you have seen earlier that the expression for entropy in accordance with Boltzmann entropy theorem is what? S equal to K ln W. And we have already calculated this ln W in terms of partition function Z. So let us substitute this value of log W in this Boltzmann theorem, and then you will get the expression for entropy in terms of partition function. So you can see S equal to K log W, and log W we have obtained, this is n log Z plus e by kt. So S is equal to K times of n log Z plus e by kt. Okay. Now let us multiply by this k to the terms inside the square bracket. So this is S equal to nk log Z and plus e by t. Here actually this k and this k will cancel out. So this is the result for entropy of a system in terms of partition function. S equal to nk log Z plus e by t. Okay. Now if you want to express this result for a system of perfect gas, you have seen earlier that a system of perfect gas at high temperature may be treated like a classical system, although that may be treated like a quantum system too, but at low temperature when interatomic separation is very small. But at high temperature, when the intermolecular separation is very large and the wave packets associated with the molecules of a perfect gas do not overlap, then the molecules of a perfect gas are treated indistinguishable, and they follow the concept of, they follow the rules or laws of classical statistics, and that is treated like a classical system. So this for a perfect gas, you know that the total energy of a system of perfect gas consisting of n molecules is equal to what? This is 3 by 2 nkt. So E by T will be simply equal to 3 by 2 nk. So when we will apply this equation for the system of a perfect gas, this E by T will be replaced by 3 by 2 nk. Okay. So what will be the expression for entropy of a perfect gas? This will be S equal to nk log Z plus 3 by 2 nk. And you can take this nk as a common factor, and so S is nk log Z plus 3 by 2. This is actually the expression for the entropy of a perfect gas, although this expression is not correct. But there is a fault in this expression, which we will actually see in the forthcoming lecture in the video or titled Gibbs Paradox. You will see that when we will use this expression of entropy for a perfect gas, this will lead a invalid result. When we will talk about the entropy of mixing, the result will be invalid, that will be not correct. So this is actually not the correct expression for entropy of a perfect gas. But what will be the correct expression, what is Gibbs paradox, all these things we will discuss in the forthcoming lecture. Okay, thank you very much.